Another example on Faraday's law and Lenz's law. Here we have a rectangular loop. So the figure shows a rectangular loop of wire immersed in non-uniform and varying magnetic field B that is perpendicular to and directed into the page. So the direction of the magnetic field into the page. The field's magnitude is given by B equals 4 multiplied by t squared multiplied by x squared. Here we have the magnetic field is a function of time and space. So it is varying in both in time and space. With B in Tesla, t in seconds, and x in meters. Note that the function depends on both time and position. The loop has width W equals 3 meters. Its width in x direction is 3 meters and height h equal 2 meters. Its height in y direction is 2 meters. What are the magnitude and direction of the induced EMF around the loop at time t equals 0.1 seconds? Okay, as we said from Faraday's law, the induced electromagnetic force is minus partial phi b by partial t, and phi b is the total flux passing through this loop. We note that if the field is varied in position, we cannot make multiplication. We must use integration to get the flux through the loop. So in this case, the flux is the integration of the magnetic field B dot the area dA. And because the normal to the area in the same direction of the magnetic field, so the angle between these two vectors is 0. So it would be the magnitude of B multiplied by the magnitude of area, d area, cosine 0, so cosine 0 would be 1. So we don't need to make dot product, vector dot product here. We can make conventional product, B multiplied by dA. Now the value of B is 4t squared multiplied by x squared. What about the delta area? As we see, the magnetic field here is varying with B, with X. The magnetic field is varying with X, but is not varying with Y. So we can assume the incremental area is this yellow strip, which has a height h and length delta x. So we are going to integrate on x, which is varying in the magnetic field, but y is constant. So delta area dA can be replaced by h multiplied by delta x, the area of this strip. We start with the strip, so since that we can approximate the field as being uniform. So in this case, this is the delta area. And the value of B is 4t squared x squared multiplied by h multiplied by dx. Now we are going to integrate this for x starting from 0 to w, and we have w equals 3 meters. So the total flux inside the loop would be 4t squared h. All these items are independent on x. Integration of x squared dx, and the limits of integration from 0 to 3. From 0 to 3. The integration of x squared is x cubed over 3. and applying the limits of integration from 0 to 3. So this would be 3 cubic over 3. So it is 27 over 3. It is 9. 9 multiplied by 4 multiplied by the h multiply h. The value of h is 2. So 4 multiplied by 2 is 8 multiplied by 9, which is out of this integration. So 8 multiplied by 9 is 72 t squared. So this is the total flux inside the loop as a function of time. Now by differentiating the flux inside the loop with respect to time, we obtain the induced electromagnetic force. The induced electromagnetic force would be d phi b over dt. So in this case, it would be d phi b is 72 t squared over dt. 72 is a constant. The differentiation of t squared is 2t. So in this case, the induced electromagnetic force would be 144 t. Now by applying t equal 0.1 second, we can find the induced electromagnetic force at 0.1 second is 144 multiplied by 0.1, so it is 14.4 volts. This is the value of the induced electromagnetic force inside the loop due to this time varying magnetic field. The question now, what is the direction of this induced electromagnetic force? To find out the direction of the induced electromagnetic force, we can find out this value of B is increasing with time. So as the time increases, the value of B is increases, and the value of B is going inside the page. So the induced electromagnetic force will introduce induced current and magnetic field, which opposes the increase of the magnetic field inside the page. So the induced magnetic field would be outside the page. So if it is outside the page, and according to the right hand rule, so the current in this case would be counterclockwise. So the induced electromagnetic force in this case would be counterclockwise. Counterclockwise. Okay? Alright.